In this video, we'll cover the basics of how different machine learning methods can be trained for image recognition. Note that I assume that you have some basic knowledge about different machine learning methods. I have a bunch of simple videos about machine learning on my homepage if you'd like to watch those. We'll first see how simple methods like decision trees and logistic regression can be used for image recognition. Then we'll see how to use a basic neural network and how a convolutional neural network works. Finally, we'll see how a number of machine learning methods perform on the classical MNIST dataset. Suppose that we have taken a picture of this number and a picture of this number. A picture consists of a grid of pixels. For example, this image has 4 pixels in width and 5 pixels in height. In total, the image therefore consists of 20 pixels. Each pixel has a certain value that corresponds to its brightness. The values usually span between 0 and 255. In this example, high numbers represent a black color, whereas low numbers represent a gray color, and the white background is represented by zeros. Note that black color is usually represented by low numbers and white with high numbers, but for the purpose of this video, white color is here represented with zeros, because it is then easier to identify the white background. If we have a grid with numbers like this, we can create the corresponding image with a software, such as R or Python. A color image is represented by 3 layers or grids, which represent the brightness of red, green and blue color. The combination of the numbers in the 3 pixels then gives a certain color. To explain image recognition in the simplest possible way, we will here use only 2 colors for our images. The corresponding numerical matrices hold normalized values, where the 1s represent the orange color, whereas the zeros represent the white color. We will here have a look at how a decision tree can be used for image recognition in order to identify if an image includes an odd or an even number. To create this decision tree, I have used the following training data, which contains 5 images of even numbers and 5 images of odd numbers. Training a decision tree based on these images will generate the following simple tree. This node makes a decision based on a pixel in the 4th row, first column, whereas this node makes a decision based on the pixel located in the 1st row, 3rd column. Let's see how the tree predicts the 10 images. Since this image has a pixel with color in the 4th row, 1st column, its value is greater than 0.5. which means that it correctly predicts that the image contains an even number. The same is also true for these images. Since this image has a white color at this position, which means that its value is less than 0.5, we move to the right and check the condition of the 2nd node. Since there is a color in the 1st row, 3rd column, that means that its value is greater than 0.5, which means that we move to the right and that the image will be classified as containing an odd number. The same is also true for these images. Finally, since this image has a white color here and a white color here, it will be correctly classified as an even number. This simple tree correctly predicted if the 10 images contain an even or an odd number by just using 2 pixels. We can also use logistic regression to predict if an image contains an odd or an even number by using the 2 pixels that were used by the decision tree. We can train the logistic regression model, which means that we will obtain the following estimated parameter values. This model can be used to estimate the probability that the image contains an odd number. For example, if we would plug in the values of these 2 pixels here and do the math, we see that the probability that this is an odd number is approximately equal to 0. which means that the model predicts that this is an even number. The same is also true if you plug in zeros here. In contrast, a 0 and a 1 will result in a probability that is approximately equal to 1, which means that the model now predicts that this image contains an odd number. If we would train a logistic regression model based on all pixels, we would need to estimate, in addition to the intercept, 20 parameters that are associated with the values of the 20 pixels, which will be problematic because we only have 10 images to train on in this example. We will now use a super simple neural network to predict the same thing. The following neural network, without any hidden layer, was trained to predict if the image includes an even or an odd number. Every input node represents a value of a certain pixel in the image. For example, this node takes the value of the pixel in the image that is located in the first row, first column. This image will hold the value 1 in this pixel, whereas this image will hold the value 0 for the corresponding pixel. This input node takes the value of the pixel in the image that is located on the first row, second column, whereas this input node takes the value of the pixel in the image that is located on the fifth row, third column. In this example, I have used the logistic activation function for the network, where Z represents the weight of the bias plus the sum of the products of the weights and the input values. Let's say that we would use the network to predict if this image contains an odd or an even number. We would then plug in the pixel values in the corresponding input nodes. And sum the first weight times the value of the first input node with the second weight times the value of the second input node, and so forth, until we have done this for all the weights. Then we plug in the computed value here and do the math, which in this case results in a value that is approximately equal to 1. If we would compute the same thing for the odd output, the probability would be equal to approximately 0. Since the output value is larger for an even number compared to an odd number, the network will predict that the image contains an even number. Let's try to understand how the network predicts. Note that if a weight has a large negative value, and where the input node is equal to 1, that will reduce the value of Z, which will reduce the probability. For example, if the pixel on the fourth row, first column, is equal to 1, this will reduce the probability that it is an odd number because the associated weight is a large negative number. In comparison, the corresponding weight for an even number is instead a large positive number, which will increase the probability that it is an even number. This makes sense because 4 out of 5 even numbers have a color in this pixel, whereas no odd number has a color in this pixel. In contrast, the weight associated with the pixel in the second row, third column, is associated with a large negative value for an even number because no even number has a color in this pixel, whereas at least one odd number has a color in this pixel, which explains why the corresponding weight has a relatively large positive number associated with the odd output. Since none of the images have a color in the pixel in the second row, second column, the associated weights to this input node are close to 0, which means that the value of this input will have a low impact on the prediction. Pixels that cannot discriminate between odd and even numbers will therefore have a low weight on the prediction. Training a neural network means that we find the optimal values of the weights so that the network predicts as good as possible. To optimize the values of the weights, we let the network train on this data. For example, we plug in the values of all the pixels from this image in the input nodes and tell the network that this is an even number. It will then change the weights so that it predicts that it is an even number. This means that the weights associated with pixels with no color will be reduced, whereas the values of the weights associated with pixels with a color will increase a bit. Then we do the same for the next image and tell the network that this is an odd number and so forth. Watch the first video about neural networks for a more detailed description of how the weights are optimized based on some cost function. Once we have trained a neural network on images with numbers, we can use it to predict if an image contains an even or an odd number. Suppose that we would use the network to predict if this image contains an odd or an even number. We therefore plug in the numbers in the corresponding pixels. To calculate the probability that this is an even number, we plug in the bias weight here, the weight associated with the pixel on the first row, first column here, and the corresponding value in this pixel. Then we plug in the weight and the value of the second node, then for the third node, and so forth. If we sum all these terms and plug in this sum in the activation function and do the math, we will get the value that is approximately equal to 0. If we instead calculate the corresponding output value for an odd number, we see that the value is approximately equal to 1. Since the output value for an odd number is greater than the one for an even number, the network will predict that the corresponding image contains an odd number. Instead of predicting if the image contains an odd or an even number, we can predict what number that is included in the image. Suppose that we train the following decision tree to predict the actual number in the images. For example, if row 2, column 3 has a color, we move in this direction because the value in this pixel is greater than 0.5. We will therefore predict that the image contains a 1, which makes sense because this image is the only image that has a color in this pixel. Let's see if this image is correctly classified as containing a 2. Since this pixel is empty, we move to the right. And since this pixel in the second row, fourth column, has a color, we move to the left. And then to the left again, because the value of this pixel is less than 0.5. Then we move to the left because the pixel in the third row, first column, has a value that is greater than 0.5. This results in that the tree correctly predicts that the image contains a 2. All images will actually be correctly classified. We will now have a look at convolutional neural networks, which are special networks that have been developed to improve image recognition. To explain the basics of convolutional neural networks, suppose that we have the following image with 25 pixels. In convolutional neural networks, one uses a so-called filter or kernel. In this example, the filter is a 2x2 matrix with some numbers. The numbers used in this filter have been optimized during the training process. The following numbers are therefore optimal for this simple example. Note that one can use several filters that may vary in size, but to keep things simple, we here use only one small filter. The filter is then placed on top of the image where we perform a dot product, which means that we multiply the values in the overlapping elements, like this. Then we sum these products and add the value in a so-called feature map. Then we slide the filter one step to the right and do the math again. We continue until we have filled the whole feature map. Then we apply some activation function on the feature map, such as the ReLU function or the sigmoid function. For simplicity, I will here use the ReLU function, where all the negative values in the feature map will be set to 0. However, since we do not have any negative values, the feature map will not change in our example. Next, we perform max or mean pooling. In this example, we use max pooling, which means that we take the maximum value of these four numbers and place this number here. Then we move the window to these four values in the feature map and place the corresponding maximum number in the pooled feature map. Finally, we create a vector of the pooled feature map. The reason why we do this is because this is the input format we need for the neural network. Suppose that we would have the following image that represents a 1. That would result in the following feature map and the following pooled feature map. Let's place the two pooled feature maps here for the two images that we have computed so far. This is the result for the image that contained a 0, and this is for the image that contained a 1. If we would compute the same thing for the other 8 images with unique numbers, we will have the following input data. Next, we create a fully connected network. To simplify the illustrations and calculations, I have not included any hidden layers. Note that one should normally include hidden layers because that will increase the performance of the network. Since our pooled feature maps have 4 values, the network will only have 4 input nodes, which reduces the computational cost compared to the simple network we used previously where we had 1 input node for each pixel. Since we like to predict 10 different digits, the network will, in this example, have 10 output nodes. Remember that this is the bias. During the training process, all edges will be associated with a certain weight. For example, these are the optimal values of the weights to predict if an image contains a 0. Let's see if the pooled feature map of the first image is correctly classified as a 0. We plug in the values in the input nodes and do the same calculations that we did in the previous network example. In this example, we use a sigmoid activation function. Let's place this output value here. Then we compute the output value that the image contains a 1. And for the 8 other digits. Since the output value is highest for the category 0, the network will correctly predict that the image contains a 0. Finally, we'll have a look at the classical MNIST dataset, which contains 70,000 images of handwritten digits. 60,000 of these images are dedicated for training and 10,000 for testing. Every row in this dataset contains data for each image. The training data has therefore 60,000 rows. Each image has a height and width of 28 pixels, which means that every image consists of 784 pixels. This means that this matrix contains 784 columns in addition to the first column, which in my example holds the labels. For example, the first row represents an image of a handwritten 5, whereas the second row represents an image of a handwritten 0, and so forth. Suppose that we like to generate an image of the data that is located on row number 6. We would then put the elements in column number 2 to 29 here. Then the next 28 elements here, and so forth. Until we have a square matrix with 28 rows and columns. This image is supposed to represent a handwritten 2. By using a software, it is easier to generate an image of the matrix. We'll now see how some basic machine learning models can predict the digits. We'll train the models based on the 60,000 images on handwritten digits, and then see how well they predict which digit it is based on the 10,000 images from the test dataset. This table shows the performance of some basic classifiers based on the test dataset. Linear discriminant analysis and decision trees resulted in an accuracy of around 88%. Training these classifiers only took a few minutes on my computer. A multi-class logistic regression model performed a bit better, but took a long time to run. A simple artificial neural network with 784 input nodes, one for each pixel without a hidden layer, resulted in an accuracy of 92%. K nearest neighbor and Randolph Forest resulted in 97% accuracy, whereas the support vector machine had an even higher accuracy. However, different types of convolutional neural networks may reach an accuracy of more than 99% on the MNIST dataset. This is why these types of networks are the most common methods for image recognition. This was the end of this basic video about image recognition. Thanks for watching.